Welcome. Today we are going to discuss level trees. So if we have any tree T with n vertices, if the vertices of T are assigned integers from the set 1 up to n such that no two vertices receive the same labels, we call T as a level tree. Now if we have two level trees with vertex set as V and E and V and E dash, then we say that they are distinct if E and E dash are not the same. For example, I have one tree here. I label the vertices as 1, 2, 3. I have another tree here. I label the vertices as 1, 3, 2. So here the edge set is 1, 2 and 2, 3. Whereas here the edge set is 1, 3 and 3, 2 or 2, 3. So here in this case, E and E dash are not the same, hence we will call this T and T dash as distinct trees. And we have this very interesting theorem. It says that every label tree corresponds to a unique vector S with components S1, S2 up to Sn minus 2, where Si is in this set for each I from 1 up to n minus 2. So, to prove this, we consider a label tree. So let T be a label tree. And we pick the set of terminal vertices of T. So let W be the set of terminal vertices of T. Now we arrange the vertices in W such that their labels are in increasing order. Assume W1 be the first element of W. And we find the label, since it's a terminal vertex, W1 is a terminal vertex, so there is a unique vertex in T which is adjacent to this W1, and hence we find the label of that unique vertex. So we find the label of the unique vertex adjacent to W1, and we call that label as S1. Call the label of that unique adjacent vertex to W1 as S1. Then we delete W1 from T. So what do? We delete W1 from T to obtain another tree, call it say T1, and assume that W1 be the set of terminal vertices of T1. And once again we arrange elements of W1 such that their labels are in increasing order. And assume W2 be the first element of W1. And once again, as previously done, we find the label of the unique vertex adjacent to W2, and we call it is S2. We repeat this process until Sn minus 3 has been defined. And at this stage, we have a tree with only 2 vertices such that their labels are P and Q. Assume P is less than Q, then we mark Sn minus 2 is equal to P. And hence, we have that unique vector S1, S2 up to Sn minus 2, where Si are from this set for each I from 1 up to n minus 2. As an example, consider this tree. This is a label tree. So we pick the set W of terminal vertices such that the labels are in increasing order, and hence we have this is a terminal tree with label 5, 6, 7, 8, 9, 10, 11, and 12. So this is 5, 6, 7, 8, 9, 10, 11, and 12. This is set W. Now we pick this one and we find the unique vertex adjacent to vertex 5. And the unique vertex adjacent to vertex 5 is 1, and hence we call S1 as 1. So what do we do? In the next stage, we delete this. This is my W1. So we delete W1 from the tree. So if I delete this W1 from the tree, I again pick the set of terminal vertices. So now the terminal vertices are 1, because now this vertex becomes a terminal vertex. So here I have 1, 6, 7, 8, 9, 10, 11, and 12. And here I have W2 is equal to 1, and I find the label of the unique vertex adjacent to 1. And the label of the unique vertex adjacent to this vertex 1 is 4. Hence, my S2 is equal to 4. In the next stage, I delete this vertex 1 from the tree. And once again, we find the set W2 of terminal vertices. So the set W2 of terminal vertices is now 6, 7, 8, 9, 10, 11, and 12. And we mark this as W3, 6 is W3. We find the label of the unique vertex adjacent to vertex 6, and we call it S3. So S3 is 2. As we can see here that the label of the unique vertex which is adjacent to vertex 6 has label 2. So this is S3 is equal to 2. And as done previously, we delete this vertex from the tree and we find the set W3 of terminal vertices. So the set W3 of terminal vertices is now 7, 8, 9, 10, 11, and 12. And the vertex adjacent to vertex 7 has label 2. So S4 is 2. And we delete this vertex 7 as well. And now we have this set W4 of terminal vertices is 2, because now 2 becomes a terminal vertex. So 2, 8, 9, 10, 11, and 12. So we find the label of the unique vertex adjacent to vertex 2, and the label of the unique vertex adjacent to vertex 2 is 4. So S5 is 4. And we delete this vertex 2 from the tree T. Once again, we find the set W5 of terminal vertices. So it is now 8, 9, 10, 11, and 12. So we find the label of the unique vertex adjacent to vertex 8, and the label of that vertex is 3. Hence, S6 is equal to 3. And we delete this vertex from the graph, and so on. If we continue this process, we will have S7 is equal to once again 3, S8 once again 3, S9 is 4, and at this stage we will have the tree consisting of two vertices, this 4 and 12. If we reach to this stage and we keep on deleting the terminal vertices, then at the end we will be left with only this part of the tree. The label of this vertex is 4, the label of this vertex is 12, hence S10 will be considered as 4. So the unique vector which is associated with this tree is S1 is 1, we have computed S1 which is 1, S2 is 4, S3 is 2, S4 is 2, S5 is 4, S6 is 3, S7 is 3, 3, 4, and 4. And this is the unique vertex, unique vector, which is associated with this label tree. Now we consider the reverse implication of the previous problem. And it says that every vector with n-2 components, where each component is an element of this set, corresponds to a unique label tree with n vertices. And in the previous problem, we observed one thing, that while we were constructing the unique vector S corresponding to the tree, if the degree of any vertex was, say, di, then the label of that vertex appeared di minus 1 times in the vector S. Hence, if I have a terminal vertex, so it's of degree 1, and hence the labels of terminal vertices will not appear in the vector S, because if we subtract 1 from the degree, so it means that the labels of the terminal vertices will not be appearing in the vector S. Now you utilize this fact to prove the reverse implication, and hence we consider let Vi is the first element in N, first element in N that is not in S. Similarly, V1, V2 is the first element in N minus V1 that is not in S minus S1, where S minus S1 is obtained from S by deleting S1 from the vector S. Similarly, V3 is the first element in N minus V1, V2 that is not in S minus S1 minus S2. where S minus S1 minus S2 is obtained by deleting S2 from S minus S1, and so on. We continue this process. So the process is repeated until we obtain this set V1, V2 up to Vn minus 2. Because for each deletion of an element in S, we introduce a vertex, we introduce a label vertex. So since there are n minus 2 components in the vector S, so after deleting all the elements of S, we will have Vn minus 2 components or vertices. The two remaining vertices are X and Y. And now what do? We join Vi with Si and X with Y to obtain the unique label tree corresponding to this vector. This is elaborated in the next example. Here the vector has 10 components, so we are looking for a label tree with 12 vertices, because here I have 10 components in the vector S, and hence the set N would be 1, 2, 3 up to 12. Now if we look at the elements of S, the elements of S are 1, 2, 3 and 4, and we pick the first element in N that is not in S, and hence this would be 5. Okay, that is 5. So we call V1 is equal to 5. And we join, so S1 is 1, this is S1 is equal to 1, because we can see that S1 is 1. So S1 V1 is an edge in the tree. This is the first observation. Now what do? We consider this set N minus V1. So N minus V1 is 1, 2, 3, 4, 6 up to 12. This is my N minus V1, and the elements in S minus S1 are 4, 2, 2, 4, 3, 3, 3, 4, 4. And the elements of S minus S1 are 2, 3 and 4. So the first element in N minus V1, which is not in S minus S1, is 1. Hence V2 is 1. And we join, this is my S2, so we join 4 with 1 to have another edge. So I have S2, V2 is an edge in the tree T. So S2 is 4, V2 is 1, so that's another edge. At the next iteration, we have N minus V1, V2, and the set becomes, we delete 1 and 1 is V2, V1 is 5, so we delete 1 and 5 from this set to obtain 2, 3, 4, 6, 7, up to 12. We delete S2 as well from this set to have this set 2, 2, 4, 3, 3, 3, 4, 4. And now the elements of S minus S1 minus S2 are 2, 3, and 4. And the first element in N minus V1, V2, that is not in S minus S1 minus S2, is 6. Hence, V3 is equal to 6. And S3 is equal to 2. So, we have V3, S3 as an edge in the tree. And if we complete this process, we will have the edges 1, 5, 4, 1, 2, 6, and so on. So I have this vertex 1 adjacent with vertex 4 from this one. From this one, I have vertex 1 adjacent with vertex 5. From this one, vertex 2 adjacent with vertex 6, and so on. So if we complete this process, we will have the tree as explained in the previous example. And we have this very important theorem on label trees. It is known as the Cayley's theorem, and it says that the number of distinct label trees with n vertices is n to the power n minus 2. And the proof from the previous two theorems is not very difficult. We know that a vector S with S1, S2, Sn minus 2 components of n minus 2 components from the set n 1, 2 up to n can be formed in n power n minus 2 ways. Because if I'm constructing this vector of n minus 2 components from this set with n elements, so for each component I have n choices. So the total number of ways is n power n minus 2. And since we know that there is a bijection, since there is a bijection between the set of all label trees with n vertices and the set of these vectors. Since there is a bijection, hence the total number of label trees with n vertices is n power n minus 2. And this is the proof of the Cayley's